This is the third and last part of the lesson 5 dedicated to the mixture of gases. Now we want to introduce a special case, that is the mixture of air and water vapor at ambient conditions. This mixture is, in other words, the humid air we are used to deal with when we treat the climatization of a space. Differently from the very general case, for this application we can use tools or even empiric formulas. Here we give you an introduction only, since the argument is specific and complex. I would suggest you to refer to different and more specific sources for a deeper knowledge of the matter. Finally, we say a couple of words about the interpolation method. This method is useful when gas or mixture properties are known by a table, also by a discrete sequence of data. We will treat both the one-dimensional and the bidimensional case. I will assure you it is very interesting. Let's start. As we have said already in the introduction, we treat here the case of vapor and gas mixture being a special one, the humid air. At ambient pressure, that means from 80 to 100 kilopascal, more or less, and temperature -20 till 60 degrees. For such a case, there are existing applications and empiric formulas. Their use is very common in the ventilation design. For a specific location, the pressure is constant, depending only upon the altitude, and the thermodynamic variables are only three: the mass m or the volume capital V or their flows, the dry bulb temperature, the specific humidity, that is for definition the ratio between the mass of the water and the mass of the air. Alternatively to the last two, they can be used any other couple of variables among the density of the air, the wet bulb temperature, the dew point temperature, the relative humidity, and the specific enthalpy. As example, we solve here a ventilation problem using two methods. Method number 1 is by means of empiric formulas. Method number B is by using an application. Here is a link that you can also find in the video comments, but there are also many others available and free on the web. The problem is, given a location altitude, for instance 1000 meters, and given the airflow of the stream A, 10,000 cubic meters per hour, its temperature 35 degrees and its relative humidity 40%, we need to cool this flow up to 16 degrees and to 100% of relative humidity. Then we have an airflow B of 5,000 cubic meters per hour, and its temperature is 23 degrees and the humidity 60%. We need to find the power to cool the flow A from the state 1 to the state 2 and the temperature and relative humidity of the state 3 when the two flows A and B mix together. The method A says using empiric formulas. We introduce the formula 47 that displays the ambient pressure as function of the altitude Z, where P0 is the standard pressure, alpha and beta are constants, here displayed. For the altitude 1000 meters, the pressure is calculated, 89.87 kilopascal. Then we introduce the formula 48, saying the specific enthalpy of the mixture as a function of temperature and specific humidity. Its dimension is kilojoule per kilogram, where X is specific humidity that we can express also as ratio among the densities of the steam and the air, and it can be found from the pressure, the temperature, and the relative humidity as further displayed. The formula 49 says the saturation pressure of the steam as function of the temperature. For 35 degrees, the saturation pressure is 5.63 kilopascal. The relative humidity is, for definition, the ratio between the pressure of the steam and its saturated pressure at the given temperature. Solving for the pressure of the steam, we can get this value, 2.25 kilopascal. The pressure of the air is the difference of the total pressure, calculated already above, and the pressure of the steam, therefore 87.62 kilopascal. The density of the air can be obtained by using the state equation, and we find in this example 0.99 kg per cubic meter. The density of the steam can be also calculated using the state equation for the steam, and we find 0.016 kg per cubic meter. The absolute humidity can be then calculated 1.6 into 10 to minus 2 dimensionless. By using the formula 48, we can now calculate the enthalpy of the mixture for the state 1, and we find 76.02 kJ per kilogram. Repeating the same procedure for the state 2, we find for the humidity 1.28 into 10 to minus 2, and for the specific enthalpy 48.51 kJ per kilogram. To answer the first question, also the power needed to cool the mixture, we need to multiply the mass flow and the differential enthalpy, while the mass flow is the product of the density and the volumetric flow. We have all the data, and the result is negative 75.7 kilowatt. When the flows A and B mix together, then the enthalpy or its flow is not changing for the energy conservation, as well as the humidity is not changing for the water mass conservation. For the flow A, we can write enthalpy flow equals mass flow times specific enthalpy, and we find 133.5 kilowatt. For the flow B, we find, using the empiric formulas, both the absolute humidity XB and the specific enthalpy HB, and also we can find the density using the state equation. The enthalpy flow HB is then the product of the mass flow and the enthalpy, and we find 76.7 kilowatt. The specific enthalpy and humidity of the state 3 is then capital HA dot plus capital HB dot divided by the sum of the mass flows, and we find 15.13 kJ per kilogram. The absolute humidity X3 is the pounded average of the absolute humidities, 1.25 into 10 to minus 2. Solving the formula 48 for the temperature, we get T3 equals 18.4 degrees. Then, with the formula 49, we calculate the saturated pressure of the steam, that is 2.12 kilopascal, and to find the relative humidity, we need now only the pressure of the steam, that we can calculate by using the Dalton law, the formula number 50. In our case, PMA and PMS are the molecular weights of the air and the steam respectively. X is the absolute humidity and P the total pressure. The result is for PS 1.77 kilopascal. Therefore, the relative humidity is the ratio between PS and saturated pressure, 1.77 over 2.12, 83.4%. We represent now all the states of our example in the psychrometric chart. In the psychrometric chart, the horizontal axis displays the dry bulb temperature, while the vertical axis the absolute humidity X. All the other thermodynamic parameters can be also read in the chart. What is missing is only the flow rate. Let's start now the method B, that is using the tool fly carpet. This tool is using the psychrometric chart and can calculate automatically the states. Given the states 1 and 2 with the flow A having 10,000 cubic meter per hour, the tool can calculate the cooling load, that is 76.7 kilowatt. With the same tool, we can also calculate the state B, corresponding to the temperature 23 degrees and 60% relative humidity, when the two flows A and B mix together, being the flow B 5000 cubic meter per hour, the result is 18.3 degrees and 84.3%. As we can see, there is a small deviation, but negligible in comparison with the method A. The last argument of this lecture is the interpolation. The interpolation is a mathematical approximation to determine the value of a function in a point within an interval, knowing the values of the same function at the limits of the interval. The approximation can be linear or not, but we use only the linear one. The smaller is the interval, the more accurate is the interpolation. The interpolation can be one-dimensional if the point has only one coordinate, or bidimensional if the point has two coordinates. It is used for the thermodynamic functions known by a table, for instance the steam taps, or by a chart like the psychrometric diagram that we have seen already, or for any other function known experimentally by specific values. The procedure for the one-dimensional interpolation is: we write the equation of the line crossing the two known limits and we calculate its value in the searched point. This is the formula to be used. For the bidimensional interpolation, we write the equation of the line crossing the two left limits and then the line crossing the two right limits. We calculate their value in the searched coordinate. There are two values, and then we write the equation of the line across the two found points for the given x coordinate. And those are the corresponding formulas. Let's do an example, first with the one-dimensional interpolation. The application is for a steam tub in the saturated region. Our task is to find the evaporation enthalpy H as function of the temperature T. The searched value is the enthalpy for the temperature 112 degrees. The known values are given in the table at the right side. Temperature T1 100 degrees and the corresponding enthalpy 2256.1 kJ per kilogram. Temperature T2 120 degrees, the corresponding enthalpy is 2202.2 kJ per kilogram. The interpolation used the formula already displayed and gives a value of 2223.8 kJ per kilogram. The exact value is slightly different. Let's do now an example of the bidimensional interpolation. The example is given from the psychrometric chart. The task is to find the enthalpy as function of temperature and relative humidity. The searched value is 36.5 degrees and 52%. The known values are those ones. Point A, temperature 35 degrees, HR 50%, enthalpy 80.80 kJ per kilogram. Point B, temperature 40 degrees, humidity 50%, enthalpy 100.81 kJ per kilogram. Point C, temperature 35 degrees, humidity 60%, enthalpy 90.23 kJ per kilogram. Point D, temperature 40 degrees, humidity 60%, enthalpy 113.47 kJ per kilogram. As the procedure, we calculate first the enthalpy corresponding to the wanted temperature at the left boundary for the humidity 50%. We calculate then the enthalpy for the wanted temperature at the right boundary of humidity 60%. Then we calculate finally the enthalpy at the wanted temperature and wanted humidity by using the interpolation formula of the 2 points found above. And we get 88.88 kJ per kilogram. The exact value would be 88.46, so we are very close. In this slide are resumed all the formulas used in this lecture for future and comfortable use. Thank you for your attendance. I hope you have enjoyed it. See you in the next lessons. Bye bye.